Good afternoon, everybody. My name is Andrew Ellis. I'll be talking to you about optical communications. Before we go any further, though, I need to thank everybody that I've worked with, including those I've not published papers with over the past, I don't like to say how many years. Everything that they've done's contributed to where I am today and therefore to this talk. And of course, I'd like to acknowledge funding from EPSRC and the Royal Society, who have been looking after my research over the past few years. So my slides are not progressing. There we go. In outline, and we have about 45 minutes together. I'll probably spend the first third of it talking about what the original vision was, where we've got to so far, that backseat question, are we there yet? Another quarter of an hour on what's going on right now, what sort of research to expect to see in the coming sort of 5 years or so, and then what should we expect in the long term, or at least some guess about what we should expect in the long term. So I hope each of those will be about 15 minutes long. So starting back at the beginning, arguably the beginning goes all the way back to people communicating with mirrors and smoke signals, but a nice documented beginning is back in the 1920s with Captain Eckersley, the chief engineer of the BBC, who had a vision of bringing interactive content to people's consumption of entertainment media and evolving that entertainment into something more two-dimensional. So pretty much what we're experiencing right now, and that goes all the way back to Captain Eckersley in the 1920s. Similar sorts of times, we started having some rather exciting events where they were linking together music halls, so they'd have the performance in one music hall in London, and then in some theatre around the country that have a connection. People would attend that theatre and it would be like being at the cinema, but it was viewing a live performance. And the video that you can see on YouTube for that shows everybody having a marvelous time in the two music halls. I don't know if you were watching in the top right hand corner, there was a little video from the post office showing what their vision in the 1960s was, which was of people being able to keep in touch with family who were away in different countries. The young lady was an Australian, the gentleman on the other end was a British gentleman, and how you could share documents using oscilloscope cameras and things using those technologies. So pretty much everything that we expect to see from the internet was well seen, certainly before the 60s. Moving on to today, we're here today on Zoom, Teams, Skype, etc. are also available, being able to work from home, telework and things. We have things all the way through to life-sized holograms, holographic projection, music events with holographic performers included, and that vision from Back to the Future of people using many screens to bring information in from all over the world, that really is sort of starting to happen. So all of that is happening. And what the vision is to make people's lives easier, to give them the information that they want, to enable them to be connected with the rest of the world without having to travel. So that's what the vision was. And this has been a journey very much like Moore's Law. We all know Moore's Law, that we believe that the transistor capacity doubles every 2 years or so. So we have on the x-axis time, and on the y-axis we have the log of the transmission number of transistors on an integrated circuit, and it's a nice straight line running along here on those axes. And if you look at communications capacities, either this line showing what you can get in published scientific papers, this line is what a telecoms network would be having as something that they switch within the network, so the actual line capacities would be higher, and the services offered to the general public. They're all also growing with a straight line on this linear time log capacity graph, so they're all growing like Moore's Law as well. The interesting thing is that you can get data all the way back to 1858 on wired communication capacity, and it's Moore's Law-like growth for over 160 years, even longer on the next slide. So how long is that going to go on for? Surely we've doubled, all exponentials have to come to an end. And a colleague of mine, Nisha McSweeney, pointed out a very interesting correlation to me. So what we have shown here is this purple line is the global population in billions. It's on a log scale so that we can actually see what's going on over a few centuries. And then these green points These are the compound annual growth rate on a log scale, so that's sort of doubly logged, of communication capacity. And you can see that for a very long time, there was a good correlation between the population and the compound annual growth rate. So the more people there are, one, the more things there are to find out about, the more demand there is to communicate, but also the more ability to invent a better way of doing it that there is. So our growth was increasing with the population. And then interestingly, we hit this phenomenon called the dot-com boom, where things took off. And it's just a coincidence that I like to point out that that happened with a compound annual growth rate of 40%, which is doubling every 2 years. We hit the Moore's law rate. Moore's law is actually an economic thing that says this is the best way to make money. Everything exploded, and as we know it, then a few years later, everything collapsed. And we've now recovered to Moore's law's rate. So we've got a consistent compound annual growth rate of 40%. And it's arguable that there's a gap opened up between what one might expect the population to need and what we're able to deliver. So we might need to correct that. So far from thinking that this journey is over and that we have the capacity that we want, this graph arguably says that the journey is still continuing and there's a lot more to do. And if anything, we expect to see this go up rather than start going down. So that's the Moore's rate. And Professor Andrew Lord from BT, when I was talking about this, very helpfully came up on the next presentation with this graph showing an internet service provider's traffic that they serve, showing that over the past 20 years, their compound annual growth rate's actually been about 60%. So it's been up here, a lot closer to the population for their data on a particular internet service provider. Some people would say that in the UK, due to the regulatory environment, we fell behind a little bit, and we certainly, the globe fell behind a little bit here. So this is kind of closing the gap. But it does show that we're not there yet. There is still a huge demand for increasing capacity. Huge demand for increasing capacity, great. And we are just talking about the internet. That's that little black wireless box in the cupboard under the stairs that's got a little red light on, or preferably a blue light, and it goes red when there's a problem. But we know that's not what the internet is. The internet's actually big, huge network of optical fibers and cables, data centers and things, and is actually quite large. Just looking at the energy of all of this thing that we call the internet, globally, the internet uses about the same amount of energy as the global aviation industry. So that's something that's seen as large and a threat to global warming. So the internet might be as well. And nationally, the UK energy consumption on the internet is about the same as the UK energy consumption for road traffic as well, for cars. So those are big things that are on people's radars when they're talking about climate change. And so it's reasonable that we would include the internet on that as well. But it's not big enough. Not only is there latent demand within the places that have got it to have even more, but there are many, many parts of the world where the download speed and the number of users of the internet is very, very low. There are countries where there isn't any internet at all, and average download speeds in the low megabits region. And this is something that the World Bank is looking to address, and we've been looking to address as well with colleagues at the University of Glasgow and Witwatersrand in South Africa. All through my career, I've had people from the business unit saying, but we installed a new network last year, surely you can't be talking about us having another one. We've got everything we need, and every time we come along with more capacity, we don't know what people are going to do with it, and excellent inventive people in the creative arts and industry come along with things to do with it. But you're always stuck at the back of your mind wondering, what do we actually possibly could we consume? So you can look at the human body, and in Encyclopedia Britannica, they have a page talking about information transmission rates of the senses. And you can look at the 5 senses and you can add up what a human body can actually absorb in terms of information. And it's about 11 or 12 megabits, mostly through the eyes, quite a bit through the skin, nose and ears, and a little bit through taste. And we have, of course, about 7 billion people on the planet. So you take all of that, multiply the two together, and you could imagine an 8.7 exabit global network capacity is possible to be absorbed by human beings. And we know we can build submarine cables at 250 terabits. So to meet that demand, we need just 34 submarine cables around the world. And I tell you, we have many, many more than 34 submarine cables. So that argument says that we're well past there yet. We have arrived and we've driven on past. So what's going on? Well, it's not just us. There's lots and lots of other things going on. The data centers themselves actually use more information communicating between each other and synchronizing and sorting the data than they actually have in traffic as requests for information from them. So the intra data center traffic is larger than the data center to user traffic. We have interesting things happening with smart motorways with lots and lots of sensing. We certainly would like to know if there's a traffic jam ahead so we can take a different route, but there's so much more going on there. We have smart homes, we have factories of the future, and we also have smart cities where there are so many internet connected devices and processors going on. I decided not to make that big enough for you to spend time looking at. So there's an awful lot more than just people going on with what we need to do with the internet. Note of caution on that, be careful what you wish for. The original vision was for communicating between people to make their lives easier so that if they're forcibly separated in different countries, they can keep together and have that social interaction so that companies can do business remotely and we can make the world a smaller place. I don't think that original vision was for a nice sunny day around the cathedral in Birmingham for everybody to be sitting on their mobile phones and not interacting with each other. I don't think the original vision was for people to be happy to be talking on the phone when really they want to be together, to not actually be flirting face to face, but be flirting online, to be so obsessed with internet connection that they do it whilst they're cycling along, and to have factories where there's very, very little human employment. The old man and the dog is there to keep everybody away from the equipment and the man is to feed the dog. We don't need people in factories anymore. I don't think that that sort of thing that is happening today is what we actually had as that original vision. It was to help people along. So we need to be very, very careful about it. Another way of looking at what we need, watching sport. Preferably with an atmosphere from a crowd, which in the UK is slowly starting to come back. And the rules say that this massive stadium, looks like the Bernabeu to me, would only have 2,000 people in it if it was in the UK rules. To do this, we've got 4 people watching it. So one argument says that we only need 40 megabits connection to this house because that's all that those people can absorb. We have this huge ultra high definition television display that's going to be connected with HDMI 2, so it's got 18 gigabits going into it. Is either of those really what we need? I don't know. Some things to think about with that. If we were playing spot the ball, we would try and correlate where people are looking to see where they are. So let's just sort of have a go at that. And I'm useless at spot the ball. I've never won a spot the ball, so don't worry if I've got the eyes wrong. This guy is looking at the face of the person making the tackle, and he's quite impressed by that going on. He actually only needs to see the face of that guy. He doesn't need to see anything in the crowd. So we're wasting 17.6 gigabits worth of information that he's not looking at. This guy's looking at the ball, and again, we don't need the rest of the screen going on there. We know what he's looking at. This guy's looking somewhere else. I can't really see what his eyes are, so we can't tell what's going on there. And this guy's not even looking at the screen at all. So we don't need that information. However, this guy might also have been looking at something in the crowd. It's ultra high definition. He might have spotted a friend somewhere in the crowd. We don't know what it is. So what should we be doing? Should we be restricting things to 40 megabits? Should we be putting 18 gigabits through? What should we be doing there? And it's a matter of where you place the intelligence. If we put all of the intelligence with the people, then this screen needs to show absolutely everything that they would possibly want to look at, and we end up needing massive capacities for the connection. If we try and put the intelligence in the screen, what we need to do is to have 4 screens, 1 for each person, and work out what that person is looking at and where they're looking at. So we only provide 9.9 megabits worth of information where they're focusing and some peripheral vision information as well. And that needs us to sense what they're looking at. It needs us to process things with low latency, and how that would work out is quite difficult. But there are very, very interesting things to do in all areas of internet technology on where you place the processing power in order to optimize the performance. And it's an interesting calculation to see how much energy is used in processing something compared to how much information is used with transporting it, which we can go into in the question and answer if anybody's interested. And then there are questions about where you do the links. So if you remember the smart motorways, this is just a little sketch of all of the radio signals that happen in smart motorways. We have sensing going on from the infrastructure to the road, from cars to cars, and small infrastructure for self-driving going on. We have telecommunications networks, and we're connecting all of this stuff up with wirelessly anyway. E-band data links, etc., are getting used. People are even imagining doing wireless charging of devices. When you're looking at that, it's easy to do that. You can do it. It works. Actually, at the moment in the UK, there's a subsidy for doing this in some regions, and you can call it 5G, and it makes your region sound cool and a great place to come and do business because it's ahead of the curve on 5G. But that's not how you have to do it. You could connect all of your fixed infrastructure together with fibers. If you've got somewhere where somebody's parked on top of a wireless induction charger, is it really that much trouble to connect a wire in and do that wirelessly? And one can clear up the electromagnetic smog around there so much easier. You can do that as well. All you need to do that really is put in the right cable. You're at a location, this can be cabled. Here you had to put power in. You could have put fiber in at the same time, so it's just a matter of planning ahead. You can do this very, very easily. Some of the things you could switch to light to do it. You do it this way, not only do you get better, more reliable performance for the things that you've fibered up, but because you've got less usage of the spectrum, those things that do need to use the wireless spectrum are better off. And there are safety implications, not only the fact that these links are more reliable, but electromagnetic safety itself. Electromagnetic safety, you said. Did you really mean that? Unfortunately, I did. A few years ago, when 5G was starting to emerge, there was a seminar on electromagnetic safety, and I've picked one presentation out of that from Ericsson, which shows things quite nicely. He has this one slide in there where he's showing the exclusion zone from an antenna. We expect all antenna to have an exclusion zone. And the safety standards in Europe, this one here, mandate that one should consider what the antenna is capable of doing and work out where you need to be to not have, if you're a member of the public, 10 watts per meter squared, or if you're a worker who knows what they're doing, 50 watts per meter squared. The safety standard then says that there is a significant hazard associated with it, and a hazard is defined as something that can kill you in a reasonable period of time or have an effect on your fertility. So it affects future generations. And that is saying that 25 meters away from the tower at ground level, there is a hazard if you run with 5G according to the safety standards and what people would need to do to get the signal to noise ratio. Now, obviously, they're not installing that. They've been looking at modifying the safety standards so that the safety standards are considering what you will do rather than what you could do. So this slide is assuming everything is turned on full and everything is focused. That's not going to be the case. That's statistically very, very unlikely. So they're looking at modifying the standards. So there's nothing unsafe at the moment. But it does tell you that we're very, very close to safety from electromagnetic radiation being the limiting factor to what you can do with remote communications. That says that you want to put as much as you possibly can into cables, into coaxial cables, into optical fibers. But equally there, you don't want to go too far the other way. Back in the 19th century, people were putting everything into copper cables, and they had a little bit of a disaster in Boston where the telegraph poles at the top of the building carrying everything collapsed with the weight of all that copper. Bit of a major disaster. Their solution was to bury cables underground. But there's a simple practical thing of the space at collection points to worry about. So Space Division multiplexing research at the moment is primarily concerned with space rather than capacity, because obviously you can use just multiple cables to get capacity on its own. So that's where we are. That's why we still have somewhere to go on this exponential thing. But as well as actually delivering that, we need to start thinking about why we're doing it and how we're doing it. So those are things that are going on right now. In the next two sections, we're going to look at what we're doing right now. And then in the final section, we're going to look at what we could do in the future. So right now, we're looking at things like capacity and things. We have a very good understanding of capacity. For very, very many years, we've had Shannon's law, which says that the capacity that you have through a system is going to grow logarithmically with the signal-to-noise ratio and will be proportional to the bandwidth of the channel. And more recently, over the last decade or so, we've started to understand nonlinearity in optical fibers. And so for a particular system, a particular launch power will come along, and as you increase the launch power, you get interactions between the channels, which adds, in terms of intersignal, a deterministic distortion to the signal, or a random distortion to the signal if it's induced by noise. But if you don't take into account that distortion, you reduce your signal-to-noise ratio, and there is an optimum point here. These sorts of curves, called nonlinear threshold curves, and you can plot them with your achieved information spectral density or mutual information on this axis, or your bit error rate, or your quality factor or Q factor. They all have roughly the same shape, increases as you increase the signal power up to a maximum and comes down. We would tend to typically want to operate near this maximum point if we can. And commercial systems now are running very, very close to what's possible. Now, you can compensate anything that's deterministic. So if you have a channel, you know, you can calculate what that channel would do. So you can back propagate that and improve the performance a bit. And it's easy to argue, and it has been demonstrated, that even at higher powers, you can arrange how you distribute points to use any amount of power to get that same capacity. So actually this curve, whilst it goes flat, although the naive calculation would have it coming down. If you then looked at compensating all of the deterministic stuff that you could possibly know about, rather than what you typically know about, typically you know about the channel you're detecting. But if you have many, many different communication channels on the fiber, lots of different colors, they add up in an unknown way. But if you were to know what they were, so you're using an optical device which can process all of that information at the same time, such as an optical phase conjugator, or you had a multi-channel optical receiver, you then get limited by the nonlinear interaction between the signal and the noise, something that we call parametric noise amplification. And you have a shift in the peak of this nonlinear threshold curve. And again, you can design formats that go along here. I have actually seen one result from Maria Sorokina that's actually just slightly up here, which is really, really promising, because it's going into an area where I don't understand how it works. So that's quite good. And this, of course, is all normalized. So in order to increase things, you would be looking to increase your signal power by about 8 or 9 dBs in order to get 2 bits per second per hertz extra capacity. For a long haul system, that's really great, because you might have only been running at 2 or 3 bits per second per hertz capacity, and so you're almost doubling things. For a shorter reach system where you might already be running at 5 or 6 bits per second per hertz, that's hardly worth the effort of going to. But we're sitting in the labs, people are able to work up into this region here. I'm looking a bit better than the commercial systems. These are, of course, estimates. What all of that means is that if we're going to increase the capacity, we need to go from what we're doing at the moment, and maybe 5 or 6 years ago, what we were doing would be a modest constellation like 16 QAM, a limited number of ranges, just the familiar C-band from 1535 to 1560 nanometers, wavelength with WDM running on that, modest format, uniformly distributed, the minimum amount of DSP that we need. And what we do to maximize that capacity is to go here, which is just a cartoon showing that we need to increase the number of wavelengths that we use. We need more wavelengths. We need to optimize the constellation. We need to not only increase the constellation size, but those symbols that are degraded the most, we need to use them, yes, but use them sparingly and when needed. So we need to do constellation shaping. We need to improve the digital signal processing to get this sort of data out, and we need to compensate that nonlinearity. I did just check this morning, and there are sessions on all of these matters, multiple sessions on each of these points at ECOC. Some of those sessions are running right now. Some of them are running this afternoon, tomorrow and Wednesday. So if you really want to know what's going on with these things, go along and watch the invited talks and the tutorials on these topics at ECOC. I believe the recorded presentations are available to the general public, but I'm not quite sure. The other thing that we're worried about in optical communications is energy consumption. And we've been doing very, very well with the energy consumption. Taking a result from Rod Tucker here on submarine systems, we have been reducing the energy per bit remarkably since we first introduced transatlantic communications and Marconi with the radio in the first 1858 cable. And back here, 20% per annum improvement in the energy consumption of a submarine cable system, mainly by increasing the capacity. And the energy per bit has been halving every 2.5 years, so a little bit faster than Moore's law, which is great. However, the amount of data that we're using is doubling every 1.3 years. It's doubling more quickly than we can reduce the energy consumption. Now, I have to be very, very careful here. When I first said in 2015 that BT used 2% of the UK's energy consumption, BT very, very quickly and publicly slapped me down, saying that they didn't use 2% of the UK's energy consumption. They used 1.95%. So BT doesn't use 2% of the UK's energy consumption, but it uses a measurable amount, and it's something that determines them. And even if you accept that we're going to continue to invent things that use less and less energy consumption so that the energy per bit continues to halve every 2.5 years, because the capacity that they're having to deliver increases more rapidly than that, the energy use is going to double every 3 or 4 years or so. And this isn't going to happen because it can't happen, but if you were to just take that exponential line and extrapolate it, you'd find that there's a problem in 2035 when we're predicting that the energy consumption would be 100%. In the same conversation with BT, they pointed out that their energy consumption hasn't actually increased for a couple of years. So they'd started a program around about 2012, driven by energy consumption, to actually address that. And what they were doing was that they were decommissioning the oldest equipment. When I used to work for BT, we had 7 or 8 different platforms all running, because if it's not costing you anything, why stop it making you revenue? Very sound business argument. But now it is costing them things in terms of electricity. Those older systems, switching off a 140 megabit plesiochronous digital hierarchy system and replacing it with a modern 400 gigabit coherent system, probably doesn't cost you any more power at all in watts, and you've increased the capacity by orders of magnitude. And you can do very simple, naive Excel curve fits of what should happen here. So if you just kept everything as you're going along, and every new generation is 2.5 times less energy per bit, you get this sort of curve running along. But if you switch everything off and only ever use brand new equipment, you can shift that curve across by 10, 12 years. And that's exactly what BT have been doing. They've been staging when they're switching things off to give them that 10-year margin to keep the energy consumption down. So that sort of sensible thing to do is now necessary to keep the energy consumption in track. What sorts of things can we do to continue to reduce that energy per bit? At the moment, we're looking at transponders based on digital coherent technologies. So back in 2015, Mary and Simone produced this graph for me looking at the energy consumption in nanojoules per bit that you could get for various different coherent formats as a function of the transmission distance. And obviously, if you went further than that format was able to go, you had to have extra transponders coming in. So you get discrete steps coming along where you have to double the number of transponders. And you can see that as you increase the distance, the energy consumption goes up. And as you increase the modulation format, with the technology that was around at the time, higher order modulation formats were actually a bad idea. They used more energy because it was more difficult to extract the information. But things are not that simple. If you reduce the amount of energy that it takes to process a bit of information in CMOS, which happens all the time, a wise man once said, never bet against CMOS, that all changes and the curves start to go down. So whilst it was at the time very, very advantageous, maybe an order of magnitude benefit to actually stripping some of the digital signal processing out, and for example, in this particular case, rather than doing digital carrier recovery, you did pilot aided carrier recovery, you could substantially change energy consumption, reverse this higher order format is worse to higher order format is better. there comes a point in CMOS technology where doing it digitally is better. And we are getting very, very close to this point where the higher the order of the modulation format, the better you are, even when you're taking into account the fact that you need to use multiple transponders to get there. So never bet against CMOS. We need to get the CMOS working, get ourselves down into this region, and be able to operate with the higher order modulation formats. The other thing that uses power in these systems is the optical amplification, and of course you can optimize that. So typically we would work at the peak of that nonlinear threshold curve, which is this blue line here, where we're plotting the total energy consumption of the system in terms of pump power versus the repeater spacing that you're using. And we have contours of the information spectral density here. So as we increase the launch power, the signal to noise ratio gets better, then we hit the nonlinearity, it starts getting worse. We would normally be operating here. Commercially, we like to stretch the repeater spacing a little bit here. But if you wanted to, you could come all the way down to here and operate at a shorter repeater spacing for exactly the same system capacity, or even you could fully optimize the system, work with something around about 30-kilometer repeater spacings and get maybe a factor of 3 or 4 reduction in the energy consumption from that line simply by using more lower gain amplifiers. And again, there are a couple of sessions at ECOC looking at this. And even broader than that, what we're worrying about here, the energy consumption is dominated by those transponders. We have the capability to deploy 400 gigabit transponders widely. There are trials reported at ECOC on 800 gigabit transponders. So we have the transponders available. They're the latest technology. They've got the best energy consumption per bit. But if we're limited by the signal noise ratio of the system, as shown here, we have to use more of those transponders. So we're running 2 links here at 100 gigabits using transponders that would go at 400 gigabits. A colleague of mine, Felipe Ferreira, came up with this wonderful idea of twin fiber, where he says, if the fiber's in the ground, why don't you use it? And he's got an all optical technique where you can actually bundle those together and increase the signal to noise ratio of the system. So that in order to get 200 gigabits across that link, you need no extra equipment other than this optical gizmo that he invented in order to extend that. So you use all of that fiber that's in the ground to extend your technology. So this sort of innovative thing, not particularly selling this one, this is a good example. There are ways that we can come up with good inventions to use those resources that are in the ground to reduce the energy consumption of the system and or improve the overall performance of the system without having to deploy anything new. So there's plenty of new ideas around. Again, most of those are at ECOC. If you're not able to get to ECOC and you want to hear the technical details behind what I'm saying, I've put most of it in these sorts of publications. So the sort of socio-political sort of economic stuff is in this philosophical transactions paper. There's technical details in this review paper, and some of those graphs, the details behind those are in this book chapter in the book published by Wabnitz and Eggleton. So other things there. And of course, there are lots and lots of other books and reviews on these topics that you could go for. I'm just plugging my own. So that's what's going on at ECOC at the moment. That's the sort of area I'd expect to see research proceeding in the next 5 years or so. But what's coming on in the future? Well, lots and lots of things, and we can only cover some of them. So here are 7 that I'll try to rattle through in the next 15 minutes. Areas where there's things to look at. There's distance, as always, distance. There's mobility, there's latency, there's integration, there's optical signal processing again, data centers, and something completely different. So in terms of distance, going back to that Moore's law for communications graph, we have the installed systems coming along, or is that research results? We transitioned from doing things on copper. We went into optical systems. We did have a result on coherent back in the 90s. We're now into digital coherent, and we're starting to move into a space division multiplexing scenario. So these stars sort of say change of technology to optics and then to space division multiplexing. And I'm also showing the improvement in CMOS in some way or another. I know the axis says feature size, but you can also read that axis as cost of the CMOS. So at some point in time, this curve crossed down below this one. I haven't got the axes aligned properly, and it was possible to do digital coherent. It was economically viable to do that and technically capable of doing that. And we can also look at, as well as doing those core networks and those submarine networks, we can look at shorter reach networks. And indeed, we are doing so. So we already have optical access networks going on And we can already foresee that before 2030, where that energy crunch is happening, it is possible for us to start to have to rethink how we're doing those optical access networks and those shorter reach networks. But there's even shorter reach networks than that. There's in-building networks, such as data center networks, and there's in-home networks. At the moment, you would say that the CMOS that you need to deploy to enable optical links to be cost-effective in the home is too large, but CMOS always gets better. And so then putting optics in the home looks attractive to do. And even shorter links than that, when maybe putting a waveguide, putting a waveguide in is going to be the dominant cost. So maybe you wouldn't do it. Maybe you would go free space communications at even shorter lengths. So I think one of the directions that we'll see is a reduction in the distance over which we try and achieve particular capacities, as opposed to increasing the distance where we can do capacities, which is what we were doing for many, many years. Taking one of those possible applications in mind, what do we want? Well, we wanted that big football thing, or more importantly, we want families to interact together. And you're talking about children who aren't going to sit in front of a table with a few snacks. Well, if the snacks are good enough, maybe they will for a few minutes, but they like running around. We don't really want it to be a flat screen. We'd like it to be a little bit more three-dimensional, even if it's in a particular place. And ideally, it would really generally be mobile, although these mobile internet things really are quite ugly. In order to do that, if we're not going to put all those sensors in and that intelligence in the screens, that sort of virtual reality headset thing, we're going to need multi-room, bidirectional 16K video distribution around the home. We're possibly going to want particular points where we have studio quality stuff going on in order to do this three-dimensional stuff. We need to do this with fixed cameras, so you don't have unnatural posers. You don't have to be in a particular place. You can be lounging on your settee rather than sitting in front of the camera. I'm not saying that those sorts of things that we're doing right now, the Zoom sort of thing where we are sitting in front of a camera, won't continue to exist. But in order to get this vision of family interaction, you need to not exist. We have a lot of stuff in the home doing smart stuff for us. And what's happening at the moment is that we're sending everything to the server, we're recording everything, so we might as well use high definition cameras just in case you need the information. That's the attitude. So we need all of that. That is a fixed installation, so it could be fixed infrastructure, but it's all adding to the capacity. And of course, these virtual reality robots. Take all of that together, and it does not seem unreasonable to me to see that in 15, 20 years' time, you would have 400 gigabits channels in the home. You would need it to be capable of home user installation, although probably by builders, but this is your general trade builders that would be putting this in rather than the communications specialist. And the easiest way to do that is to actually provide them with one cable that does everything that they need. So putting your mains and your communications into the same cable, maybe something as simple as working out the cable and how you're going to do a socket to do this combined power data thing, so that you get to install that very, very easily, no more difficult than a rewire of the house. So that's in-home. What does that do to the network? If we're going to now have a vision of a house in the 2040s, 2050s with 400 gigabit networks in the house, well, at the moment we have 40 megabit networks, maybe a gigabit network in the house and going into the green cabinets. What we have then is within the metro network, we have electronic aggregation, merging those users together into something that's economical to then transport. So we go to 100 gigabits, and then in the core network, at the moment, aggregating that electronically again to 400 gigabits and very shortly to 800 gigabits, according to the field trials that are going on. And then in that future vision, we have 400 gigabits per user here. So now, we don't need to aggregate electronically to 100 gigabits to get something that's cost effective to route around the network optically. So we're going to be using optical routing and switching at 100 gigabits. And similarly, because these are all coming in optically, we could optically aggregate them together. So we need to invent that technology to do optical switching in the core network too. So we're sort of driving the electronic routing out with the bandwidth being there. And it's not that electronics couldn't do it, it's that it becomes cost effective to do it optically. And this is driven with an order of magnitude higher capacity, and that of course means that we need to do that that nice rainbow slide. We need ultra wideband, we need space division multiplexing, we need to improve the signal to noise ratio, we need lots and lots of digital signal processing to make that happen. So all the stuff that's going on at ECOC at the moment will enable that 400 gigabit home. Next thing that could happen, it's happening at the moment, would be mobility. This is a picture of lots and lots of happy people working on their phones. Why do we do it like this? Well, it's very, very cheap to install it. I imagine the cost of fiber to every park bench. That's not very easy to deploy. So we like using wireless technology because it's easy to deploy. It's also easy to use. These are all handheld devices without wires hanging off the bottom. It's children using them. You don't really want them to be tethered with wires. So those are two good reasons why we're going tetherless. However, as I said earlier, there is a safety problem, and that safety limit is going to limit what bandwidth that we can have, because it's going to limit the power, and then Shannon tells us that we can't go much further. Solution to that has been around since the 19th century. Indeed, Alexander Graham Bell invented a thing called the photophone. It was used by the German military in the Second World War, and there are patents in the 1960s on doing optical communications using binoculars and speakers and things, all very much similar. So free space optical communications is your solution. Why am I saying that? Here's a nice advertising slide of a Li-Fi enabled hospital. We have some patients who are looking around at some information screens for where they can go. We have some medical equipment communicating with the network. We have a medical practitioner here, perhaps assisting with the remote operation, bringing her technical expertise along while she's going along to actually perform something herself. So we want this good capacity. We don't want to constrain this with safety limits and constrained capacity. So we could do with increasing that. But if safety is the issue, you can run away if you like. Well, I've done it for you, and look at what the safety limits are. So radio frequency, that FCC limit that's adopted in Europe is about 7 milliwatts per centimeter squared radiated power at the user. And the optical system for a 3R, so you'd need a magnifying image for that to do you any significant harm, would be 5 milliwatts or 10 milliwatts per square centimeter. That's pretty much the same power. There's nothing to shout home. That's not a good enough reason to change technologies at all. So it doesn't look like safety is a consideration. But if you look at the carrier frequency in the RF system, we have carriers in the gigahertz regime, maybe in the low tens of gigahertz, going to 30, 60 gigahertz. In their optical, different ball game altogether. We're up at 200 terahertz, massively increased. On the other side, number of photons is radically different too. The radio signal, because it's a lower frequency, photon energy is lower, so you get more photons per watt, so you can get more information capacity through. Optically, you've got a lot less photons. But think about the best that you can do. The best that you can do is shot noise. Picture a Schottky there for shot noise. Look at the Shannon limit. For shot noise, you take the carrier frequency and the number of photons, and you get one, okay, let's go to 30 gigahertz, 10 bits per channel used as a normalized point for the RF. And on the same conditions, you get 50,000 bits per channel used for the optical. So the carrier frequency is the king. It's the fact that it's the frequency times signal to noise ratio that matters. And that gives us radically different practical capacities for these systems. And I'm running a little bit late. I apologize for that. Of course, we have Li-Fi at the moment. That's a step towards doing it. That shows that it's feasible. It highlights what some of the problems are. In order to really sort of displace microwave rather than be an addition to it, we need to get a roadmap to that ultimate capacity. So that means picking the best wavelength, not the most convenient wavelength. That means being able to find the users and then direct the energy to them. So being able to switch between broadcast and beam steering. That means dealing with the fact that very often visible light communications and other light-based communications get obscured by objects. So you need multiple paths to the user to alleviate the shadowing. And to get that shot noise limit, you either need single photon counting devices or you need coherent detection with a high collection efficiency. So those are really, really difficult challenges to overcome. But if you don't do that, then as Yariv and Gordon said, with direct detection, any optical system is reasonably noisy by microwave standards. And reasonably is very polite. It's very noisy by microwave standards. and so it won't displace it. And do an awful lot of other things with free space as well. You can replace optical fiber links where it's difficult to install or where there's been a failure. You can actually do aerial drops off low Earth orbit satellites where you have a longer link, and you can provide point-to-point access in interesting scenarios. Another thing that's coming around the corner is latency. It's already starting to have some interest. It's not dominating things hugely. 5G is using latency as one of these things. Latency gives you lots and lots of advantages. So you have haptic control using that sense of touch, which is actually a reasonable fraction of what the human body can interact with. High frequency trading tends to drive a lot of latency things. The closer you are to the decision, the quicker you can make the decision, the more money you're going to make. You get that bit in earlier. Driverless cars, a safety related thing. Getting the latency in there is very, very important. And of course, all of this virtual reality home thing, that needs low latency as well. The 2-second gaps that you can get if you're using satellite communication with latency are really, really irritating. So what do we need? Bell Labs have worked out for us on some applications that looked at what you could want. Some of the things that you would want to do 360-degree video with a free point of view. So we're not actually assuming anything about where the user is. We're providing that full vision dome worth of information. That needs well past a gigabit worth of capacity, but the latency is okay because it's a one-way communication. If we want to involve touch and two-way stuff, we don't need as much bandwidth, but we do need very, very low latencies for that. And you can imagine that if you wanted that interactive thing to also be high resolution 360-degree video, we'd be pushing up here into what you can't do with the bandwidth and you can't do with the latency. Some of the applications that they have on there, the very rightmost one needs the lowest latency, is actually a technology to enable internet technology. And so there's a possibility that one gets sucked into building a system to support the system itself, and we should avoid doing that. This point here is fine. It's something that we want anyway, so you might as well use that. But going to ridiculously low latencies in order to enable a particular way of doing it doesn't seem particularly sensible to me. But I can see applications emerging up in this region here. Important point to note is where can any processing that you need to do be? Here is the equivalent transmission distance in a single mode optical fiber for these latencies. So if we want to do haptic virtual reality, if we want a surgeon to actually do haptic operations, he can't be based in London doing an operation in Glasgow or based in Edinburgh doing an operation in Cardiff. He just can't. The latency is too large, and that's without worrying about the processing delays in the computers. Of course, you can use hollow core or free space, which buys you a little bit, but it doesn't buy you a huge amount. So we need to worry about where we place that intelligence in order to achieve these sorts of latencies that we can't do at the moment. Otherwise, we end up just dominated by time of flight rather than routers. Integration is something that's been coming along, and integration for function is absolutely wonderful. You do see the odd proposal for integration in order to provide interconnect. Just on a personal basis, that worries me at the moment. That's reasonable, but by the time we've got it developed, if this CMOS feature size keeps coming down, you've got 3 orders of magnitude mismatch between the size of the optics and the size of the chips. That doesn't seem like anything other than a specialist activity to me, so it's not going to be there. But integration is going to be vitally important, and to me integration is more about these two things. It's connector densities, and optical connector densities really what this is, a nice cool spectrum picture, hitting the physical size of providing that much data, and then within some of these coherent chipsets it might be processing 800 gigabits worth of data, but because it's running at 8 bits, you need to multiply that by 8. The interconnects here are massive. There's no way that you're going to do those with connectors. These connectors are a source of failure. If you have multiple connectors along the data path, you have a reliability problem. So in order to keep the size down, increase the reliability, get the bit rates up, reduce the power consumption, because driving a connector takes power, we're going to need integration. Not for some vision of doing on-chip interconnect, but in order to provide better function. So integration is going to be a key thing going on. Optical processing. The old vision, you're coming in with an optical system, you're going to do some optical processing without detecting it, you're going to take some power, you're going to be optical power, some electrical power, and you're going to get some optical outputs. If you wanted to do that with CMOS, you would have to first do an optoelectronic conversion, maybe serial to parallel convert it and come out again. It's well known that light doesn't interact very well with light, and electrons interact well with electrons, so energy consumptions in CMOS is low. Even when you add on driving those wires and those connectors, it's still substantially lower than what you can do with optics. So that's well known. Why would you do optical processing? Well, if you're not doing very, very much, then those optoelectronic interfaces start to dominate the performance. Not doing very much could be just a straight through connector. Who would do an optoelectronic straight through connector? So no operations per bit, you would do it all optically. And this paper by Tucker and Hinton shows that there is a complexity number of operations by which you are then better off to do electronic with optoelectronic conversion. So if you're doing a computer type function, you definitely want to do that electronically rather than optically. Sorry, my mouse is not moving quickly enough. But at particularly small numbers of operations, regeneration, wavelength conversion, etc., you are perhaps better off doing it optically. And as you increase the bit rate, because many optical devices are based on peak power, the energy per bit actually decreases simply by increasing the symbol rate. So higher speed, simple operations favor optical processing. So that could come along. Last two slides, data center networks. The traditional way of doing data centers is a big stack of trees, and there's been an awful lot of excellent work on cost reducing these optical links, driven by the volume of the number of them. That's great, and it's enabled a lot of things. These data centers are based on that, but there are better ways of doing it. There's optical bypaths using optical switches. So you've got elephant flows and mouse flows. Your mouse flows go through traditional networks already there. Your elephant flows go here, or completely radical things like hypertoruses, where we're using edge-based buffering rather than switch-based buffering for all of the flows, clockwork routing and things, which needs you to redesign the way that the software works in order to exploit the network, but it is a very good network. And there are lots of things in between. This was figure 6 in a particular paper. Each figure was a different way of doing the network. I had a bing. I assume that's because I'm running late. So we're nearly done. There's that one there. Just going back to this one, a little PowerPoint animation for a vision of what we're doing. What we've got is we've got an operation going on somewhere. It's coming through some processing power, and this goes to this display to the woman. Why would you do that? You actually want to get the information into that lady's eyes. So why don't you directly address the signal into her eyes somehow and cut out all of this electronics altogether? No idea how that will happen. It's a vision of what you might be able to do. And that, of course, frees up her hands to do something more useful, like carry her tools. Last thing about crystal balls, well, two last things on crystal balls. The laser was first reported in 1958, and by 1963, there was a review paper published which had 121 references, which had all of the applications in it that we're talking about. It had 60 or 70 lasers. Things move very, very quickly in the technical area. But commercial implementation is obviously much slower. We haven't done all of these things commercially yet. And one should remember that Moore's actual law isn't about technological advancement. It's about the pace at which you should release it for sale in order to maximize your profits. If you can do something 100 times better, it's brilliant, but people will buy that once. If you release doing it 4 times better every 2 years, they will keep buying new systems. So we're there. And there's Ali telling me I'm really late. So we're on the conclusion slide. What do I expect long term? I don't expect what we used to do, which is further faster, but to be doing shorter faster. I don't see us doing radio anymore. I see us doing optical wireless. I expect us to be addressing that latency question. Integration is for reliability. And we really do need to start thinking about how we're going to do a design jointly with the optics to exploit the abilities of the optics rather than just using the optics to support a design. That whole thing about being careful what you wish for is in there. The vision is to bring people together, not to keep them apart. We want to inform decision making, but we don't want people to be acting slavishly to those systems. We want to reduce air travel rather than induce business globetrotting. That was the original vision. We want to support people's real lives. We want to make it easier for them to live the real lives that they want to live and not have them go off and live in some sort of virtual life in a bubble on their own. We all know about the dangers of that now with cabin fever And we need to make sure that the information that we're providing is accurate and required, potentially curated, not an overflow of fake information. Finally, long-term research is going to happen sooner than you think. So I was talking 2040, 2050. It's probably going to be within 3 or 4 years. Things happen very, very quickly once the thing gets in there. And sorry, Ali, for taking so long. It's always slower when you do it for real than when you rehearse it. Here's a nice picture of what's important in life, wildlife. Thank you very much, everybody. I'd have 2 pieces of advice for the early career researchers. One is to have a plan. It's highly unlikely that that plan will not come to fruition, but it gives you a focus, it gives you a drive, it makes everyday paths easier. And the second one is to move quickly. That history of the laser slide shows that if you're lucky enough that you are inspired for a technical idea, it will only remain a novel technical idea for 2 or 3 years. If it is that good, somebody else will have it. If you've had it from somebody else, I'm not going to not say any of this to any other group. So the 90 people on this call have got the privilege of getting it 10 minutes before everybody else. Act quickly. Have a plan, act quickly.